All right, we're going to do a quick review of conic sections, and I want to show you a picture right here. I'm not going into the derivations on how we come up with the equations. I'm just going to give you the equations and just review how we would graph these things, these conic sections. And I brought up a picture of how conic sections got their name, and they are slices of cones. And if you slice a cone in a certain direction, like with a parabola, which we've known since Algebra 1 or Algebra 2, if you slice the cone parallel to one of the sides of the top cone and go through the bottom, then you're going to get a section that's a parabola. If you slice your cone perpendicular to the vertical axis and one cone, you're going to get a circle. And if you slice a cone without going through the base, you're going to get one cone you slice and you're going to get an ellipse. And then if you slice a cone parallel to the vertical axis and you slice both cones, you're going to get a hyperbola. So those are the conic sections that we're going to talk about really quickly on how to graph. All right, and the first one we're going to talk with is circle. A circle has a general equation of x minus h quantity squared plus y minus k quantity squared equals r squared, where hk, the point hk, is the center, and r is the radius. And if you know the center and the radius, you can graph your circle. So I'm going to graph a circle, and I'm just going to put my circle in the first quadrant here. And this would be the center, h comma k, and the radius of r. And that would be a circle. Now, h is the horizontal shift from the origin, and k is the vertical shift up. So it's nothing but a translation of the circle from the origin, centered at the origin, which is pretty cool. And then we could take, then that's a circle. We could take the circle equation and divide both sides by r squared, and we could say that we had x minus h quantity squared over r squared plus y minus k quantity squared over r squared equals 1. And what's really cool about this is that I could go to Desmos and I could graph. We'll have r centered at the origin just to play. So this would be x to the second divided by r, and I'm going to add a slider r, plus, actually it should be r squared, sorry, y to the second divided by r to the second equals 1. And there's our circle of radius 1 centered at the origin. And I could play around with r, and as r gets bigger, the circle gets bigger, and you know, and r really should go from 0 to, let's say, 5 here with a step of, doesn't matter there. So we can have a circle of any size there. Okay, now, what happens to a circle if I decide I'm going to change the equation slightly, and instead of r squared, I put an a here, and I'm going to add a slider a. And if I put b here, and I add a slider b, and I have a circle now, you can tell because a is equal to b. They're both 1 here, but I'm going to click on this, and we're going to go from 0 to, I don't know, 8. And then we'll do the same thing here. We'll go from 0 to 8. And I'm going to get rid of the circle here. Now, what happens if I increase b? That looks like that might be the stretch in the y direction, b. Do you see how that might be stretching the y direction? And then let's say I mess around with A now. That looks like that could be the stretch in the X direction. And indeed it would be. So when this is a circle, and so an ellipse equation is going to be x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. Now, this is when a is not equal to b. And for ellipses, the order of ascendancy here is that b has to be less than a, has to be b has to be greater, a has to be greater than b, which has to be greater than 0. And this ellipse is a certain shape, and that's going to be, if the larger number is under the x, it's going to be what we call the egg shape. I'm sorry, the football shape, because the bigger stretch is in the x direction. And the stretch in the x direction is going to be a. Which is the square root of this number. And the stretch in the y direction is going to be b, which is under the y, and it's the square root of this number here. And this is the football shape. And then the other form would be x minus h quantity squared over b squared plus y minus k quantity squared over a squared equals 1. And this hierarchy still applies. And so the larger stretch now in this case is going to be in the y direction. So we call this one the egg. So that one's a football. This one is the egg because it's a bigger stretch in the y department. And so the stretch in the x direction, in this case, is b, and the stretch in the y direction, in this case, is a. And when you radiate from the center, this is going to be b, and this will be a, that distance. And over here, this distance will be a, and this distance will be b. Okay, they also, these ellipses, have centers at h comma k. All right, so to graph an ellipse, first of all, the graphing form has to be equal to 1. And then what is under the square under the x is going to be the stretch. The square root of that will be the stretch in the x direction, and the square root of what's under the y will be the what's in the y direction, the stretch in the y direction. Okay, like I said, this is a very quick conics review. Interesting enough, what happens when I change this plus to a minus? Well, let's do that here. Let's change this to a minus. Well, it kind of breaks the egg, so to speak, and it takes what was an ellipse and either opens it left, cracks it in the middle, opens it up left and right, or up and down. So that's what happens when we have a plus or minus. So let's look at what a hyperbola equation is. A hyperbola equation in graphing form is going to be x minus h quantity squared over a squared minus y minus k quantity squared over b squared equals 1. Now, whichever term is positive, in this case, the x term is positive, is the direction in which it'll open. It'll open, since the x term is positive, it's going to open along the x-axis. Okay, and A is still the stretch in the x direction, and B is still the stretch in the y direction. Okay, and with hyperbolas, it's not as critical as to which one is under which. With ellipses, it is because of the foci equation, and I'm not going into the foci equation in this brief conics review, okay? So I just need us to be able to graph them and be able to solve for the implied functions inside of each of them. All right, so this is when it opens left and right, and that occurs again when the x term is positive, opens up along the x-axis. What happens then if I switch it around and I say y minus k quantity squared over a squared minus x quantity minus h x minus h quantity squared over b squared equals 1. Well, now which term is positive? Well, the term that's positive is the y. So it's going to open along the y-axis up and down. All right, and this stretch in the x direction is still what's under the x here, which is b, the square root of b squared. And the stretch in the y direction is going to be the square root of a squared, which is a. And what's interesting is the center is still hk. Now this one could be, the hyperbolas can be a little bit tricky because if this is positive, this is still k, because the k, the vertical translation will still always be with the y, and the horizontal translation will always still be with the x, even if it's negative. Okay, so let's do an example of each. So let's say I want to graph the following. 64x squared plus 16y squared equals 1024. All right, so first of all, we have to decide whether we know what this is. With circles, if you'll notice, I'll go back to that page real quickly. With circles, the number in front of each one of these is 1. These quadratics is 1, and they're the same. It's 1 and 1. If you look at an ellipse, it's 1 over a squared in front of the x, and then 1 over b squared in front of the y. So then what the numbers are different in front of each of these. So we know this has to be, first of all, it's being added, so it's a circle or ellipse, or an ellipse. And these numbers are different, so this will have to be an ellipse because it's going to have a stretch. So the first thing I have to do is set it into standard graphing form, which means I have to set this equation equal to 1 so I can see the a squared and the b squared and see what the stretches are in each direction. And I'm going to divide by 1024. Everything, 1024, 1024. And this will be x squared over 16 plus y squared over 64 equals 1. All right, now the stretch in the x direction is going to be the square root of the number that's underneath the x, which is square root of 16, which is 4. And the stretch in the y direction is going to be the square root of 64 or 18 because that's under the y. And the center in this case is going to be 0, 0 because I don't have this translation there or transformation. All right, so let's graph that. So I'm going to need to have a stretch of 8 in the x direction and the y direction. 1, 2, 3, 4, 5, 6, 7, 8. There it is. 1, 2, 3, 4, 5, 6, 7, 8 in the y direction, and a stretch of 4. 1, 2, 3, 4. 1, 2, 3, 4. So clearly this is an egg ellipse. And this distance here is 4, and this distance here is 8. Okay, now, why did we do this? For the express purpose of realizing that this here is a relation, and this equation up here, the 64, x squared plus 16y squared equals 1024 has two implied functions inside of it. This is implicitly defined, and I could find the upper half, that would be a function, and a lower half, and that would be a function, by solving for y. So I could say 16y squared equals 1024 minus 64x squared. Y squared equals 1024 minus 64x squared divided by 16 divided by 16, which turns out to be y squared equals 64 minus 4x squared. So y will equal the square root of 64 minus 4x squared, or y equals negative square root it helps if I write it correctly. I'll write it down here. Y equals negative square root of 64 minus 4x squared. Okay, and so I'm going to have two implied functions of y. So let's go to Desmos and see what happens. I'm going to get rid of these and say 64 x to the second plus 16 y to the second is equal to 1024, which is a pretty big number. And if we zoom in here, you'll see that this is definitely an egg, and it's an ellipse, has a stretch in the x direction of 4, stretch in the y direction of 8. Let's see the implied functions. We can say y equals square root of 64 minus 4x to the second. That's clearly the top of that function. And let's copy this. And we can see the bottom is the negative part. And both of those are implied functions inside of this implicitly defined relation. And we reviewed graphing an ellipse. All right. So what happens if I change this to a negative? Let's do that. And I'm going to start with let's say we have x squared over 16 minus y squared over 64 equals 1. Now, the dead giveaway that this is a hyperbola is now that this is a subtraction. Okay, and the stretch in the x direction is going to be 4. The stretch in the y direction will be 8. Okay, the center is still 0, 0. And if I were going to graph this, you do the same thing as if you were going to graph an ellipse by hand. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8 in the x direction, in the y direction. 1, 2, 3, 4, 5, 6, 7, 8 in the y direction. There are points. And then 1, 2, 3, 4, 1, 2, 3, 4 in the x direction. And instead of drawing the ellipse, you're going to draw the box that the ellipse would be in if you were going to draw an ellipse. And this imaginary box is going to help us set up the asymptotes. I don't have another color right here very handy. Actually, I do. Okay, and to set up the asymptotes, you're going to draw through the center and the corners of the box. So the asymptotes for the hyperbolas are going to go through the corners of the box and the center. There you go. And now we have to make the grand decision, does this hyperbola open left, right, or up and down? Well, that decision is made by knowing which term is positive. Well, what's positive here is the x. So it's going to open up in the x direction, in the x-axis direction. So this here will be the vertices. And we take this point and then we approach from both sides here the asymptotes. Same thing with this here on this side. And then these points right here on the top and the bottom are not part of the curve. They are just part of the guide box there. Okay, and so we have vertices, and the foci, which again I'm not concentrating in this video on, would reside over here somewhere outside, you know, the hyperbola. All right, so that would be the hyperbola. Well, there are two given. This is a implied function, or an implied implicitly defined equation. So if I started again with 64x squared minus 16y squared equals 1024, and I solved this for y, I'm going to move the 16y squared to the right. So this would be 64x squared minus 1024 equals 16y squared. And then divide everything by 16 and we get 4x squared minus 64 equals y squared. 4x squared square root minus 64 equals y. And then we have the negative square root of 4x squared minus 64 equals y. So these would be the two implied functions inside this implicitly defined equation. Okay, so let's go back to Desmos here and make this negative. Oh, there it is. You see that what that does when you make this negative is it takes the ellipse and breaks it in half and kind of opens it left and right. And now let's change these around. I'm going to go 4x squared minus 64. And do you see how that's the top half of the hyperbola? And I'm going to copy this. And that's the bottom half of the hyperbola. All right. So that is a quick review of conic sections. And when I mean quick. So we will chat with you later.